Wildfires. They're becoming more frequent, more intense, and more destructive than ever before. Across the globe, from California's chaparral landscapes to Australia's eucalyptus forests, these fiery infernos are leaving a trail of devastation in their wake. But wildfires are more than just natural disasters. They destroy ecosystems, devastate communities, and release massive amounts of carbon dioxide into the atmosphere, fueling climate change and creating a dangerous feedback loop. Yet, these fires aren't random. Their occurrence and intensity are intricately linked to natural forces, forces rooted in the very movements of our planet. From the way Earth spins on its axis to the way it orbits the Sun, these cosmic rhythms shape the conditions for wildfires. In this video, we'll uncover how Earth's rotation, axial tilt, and orbital dynamics influence wildfire behavior. We'll explore concepts like the Coriolis effect, seasonal variations, and even the impact of the Moon's phases on the spread and intensity of wildfires. To illustrate these connections, let's begin with a recent and devastating example: the Griffith Park fire in Los Angeles. This fire erupted in December 2024, consuming thousands of acres and forcing widespread evacuations. Fanned by the infamous Santa Ana winds, the Griffith Park fire spread at an unprecedented speed. These winds, driven by Earth's rotation and local topography, carried embers across vast distances, igniting new blazes and making containment efforts nearly impossible. Sudurtivity. But the Griffith Park fire isn't an isolated event. It's part of a much larger picture, a picture shaped by the dynamic systems of our planet. Understanding these systems is crucial, not just for combating wildfires, but for adapting to the challenges of a rapidly changing climate. In the next sections, we'll explore these connections in greater detail, beginning with how the Earth's rotation creates wind patterns that fuel wildfires. Stay tuned as we uncover the science behind these fiery forces. Let's dive into the science and discover how the movements of our planet are intertwined with one of nature's most destructive phenomena. To truly understand how Earth's rotation influences wildfires, we must start with a fundamental yet fascinating concept: the Coriolis effect. This phenomenon, though often invisible to us, is a driving force behind many of the atmospheric patterns that shape wildfire behavior across the globe. The Coriolis effect is a direct result of Earth's rotation. Imagine standing on the equator and tossing a ball directly north toward the Arctic Circle. While the ball may appear to travel in a straight line, Earth's rotation beneath it causes the ball to veer to the right. This deflection, caused by the spinning of our planet, is the Coriolis effect. In the northern hemisphere, it pushes moving air and water to the right, while in the southern hemisphere, the deflection is to the left. But why does this matter for wildfires? The answer lies in the way the Coriolis effect shapes global wind patterns. Winds are critical drivers of wildfire spread. When a fire ignites, the direction and speed of the wind determine how quickly and how far it spreads. The Coriolis effect, by influencing wind patterns on a planetary scale, becomes a key player in the dynamics of wildfires. Consider the trade winds, which are steady easterly winds created by the Coriolis effect. In regions like the tropics, these winds can fan flames across vast expanses, particularly during dry seasons when vegetation is already primed to burn. Similarly, westerly winds in mid-latitudes, also influenced by the Coriolis effect, contribute to wildfire risks in places like California and Australia, where the alignment of dry conditions and wind direction can create catastrophic fire events. One of the most dramatic examples of the Coriolis effect's influence on wildfires is the role it plays in shaping regional wind patterns, such as the infamous Santa Ana winds in Southern California. These hot, dry winds originate from high-pressure systems over the Great Basin. As air flows toward lower-pressure areas along the coast, the Coriolis effect deflects these winds, funneling them through mountain passes and canyons. The result is a powerful, accelerated wind that has a profound impact on wildfires. During the Griffith Park fire of December 2024, the Santa Ana winds were a major factor. Gusts reaching up to 70 miles per hour carried embers far beyond the initial fire zone, igniting spot fires miles away. Firefighters described the scene as chaotic, with flames spreading faster than containment efforts could keep up. The wind's power, amplified by the Coriolis effect and local geography, turned what might have been a manageable blaze into a full-scale disaster. Beyond large-scale wind systems, the Coriolis effect also impacts smaller, localized wind patterns. For example, in mountainous areas, wind directions can shift due to the interaction of the Coriolis effect with topography. These shifts create microclimates that can accelerate wildfire behavior. One such phenomenon is the creation of fire funnels, narrow upward drafts of air that intensify flames as they rise. These localized effects further demonstrate how Earth's rotation indirectly shapes wildfire dynamics. The Coriolis effect also plays a subtle but significant role in creating weather systems that influence fire risk. Hurricanes, cyclones, and large-scale storm systems, all steered by the Coriolis effect, can bring prolonged dry conditions to certain areas while dumping excessive rainfall in others. For instance, during an El Niño event, shifts in atmospheric pressure and wind patterns, partly governed by the Coriolis effect, often lead to drier conditions in the western United States. These dry spells create ideal conditions for wildfires, as vegetation becomes parched and prone to ignition. But while the Coriolis effect contributes to fire risk by shaping wind patterns, it also offers opportunities for better wildfire prediction. Meteorologists use knowledge of the Coriolis effect to model wind behavior, helping fire crews anticipate how flames will spread. For example, during the Griffith Park fire, advanced weather models were used to predict how the Santa Ana winds would evolve over several days. This information allowed firefighters to position resources more effectively, potentially saving lives and property. Despite its critical role, the Coriolis effect is often overlooked when discussing wildfire behavior. However, understanding its influence is essential for both prevention and response. By recognizing how Earth's rotation shapes wind and weather, we can better predict fire behavior and develop strategies to mitigate its impacts. Looking ahead, the interplay between the Coriolis effect and human-induced climate change poses new challenges. As global temperatures rise, wind patterns are shifting in unpredictable ways. High-pressure systems are becoming more persistent, and extreme weather events are occurring with greater frequency. These changes are amplifying the effects of the Coriolis force, creating conditions that make wildfires more intense and difficult to control. The story of the Coriolis effect is a reminder of how interconnected Earth's systems are. It's a chain reaction. The planet's rotation influences the wind drives wildfires, and wildfires, in turn, release carbon dioxide into the atmosphere, further altering wind patterns and climate. This delicate balance underscores the need for global action to address both the natural and human factors driving wildfire risks. As we continue our exploration of Earth's movements and their impact on wildfires, let's shift our focus to another critical aspect: the day-night cycle and how it affects fire behavior. Earth's rotation, the very phenomenon that gives us day and night, profoundly impacts wildfire behavior. While it might seem like a simple rhythm, sunrise to sunset, this cycle triggers changes in temperature, humidity, and atmospheric conditions, all of which play a crucial role in shaping the life cycle of a wildfire. Let's start with the daytime. As the sun rises, its heat begins to warm the Earth's surface. This heating causes air near the ground to rise, creating vertical air currents. During this process, temperatures steadily increase, while humidity levels drop. Dry, hot air strips moisture from vegetation, turning it into fuel for wildfires. Under these conditions, even a small spark, caused by lightning, human activity, or a stray ember, can ignite a fire that rapidly grows in intensity. In regions like California, daytime temperatures during wildfire season often exceed 90 or even 100 degrees Fahrenheit. These high temperatures, combined with dry conditions, create what scientists call a fire weather window. It's a period when everything aligns for a wildfire to start and spread. The Griffith Park fire in December 2024 is a prime example. By midday, rising temperatures and dropping humidity made the dry vegetation in the area extremely flammable. When the fire ignited, it quickly consumed the parched landscape, leaving little chance for firefighters to control it. But temperature and humidity are only part of the equation. During the day, the sun's heat also affects the atmosphere's stability. As warm air rises, it creates what are known as convection columns. These columns of rising hot air can act like chimneys, pulling flames and embers upward. Once these embers reach the top of the column, strong winds can carry them far beyond the main fire, igniting new blazes miles away. This phenomenon, called spotting, is a major reason why wildfires can spread so quickly and unpredictably. The day-night cycle doesn't just affect what happens during the day, it also influences how wildfires behave after the sun sets. As Earth continues its rotation and night falls, temperatures begin to drop. Without the sun's heat, the ground cools rapidly, and humidity levels start to rise. These cooler, wetter conditions can slow the spread of a wildfire, providing a temporary reprieve for firefighters. This cooling effect, however, is not always guaranteed. In some cases, especially in areas like Southern California, the benefits of nighttime cooling are offset by strong winds that persist through the night. The Santa Ana winds, for example, are known for their ability to blow hot, dry air across the landscape even after sunset. During the Griffith Park fire, these winds continued to fan the flames throughout the night, making it nearly impossible for firefighters to establish control lines or contain the fire's spread. Another nighttime phenomenon that impacts wildfires is the collapse of smoke columns. During the day, the heat from a fire keeps smoke rising high into the atmosphere. But at night, as the air cools, these columns lose their upward momentum and collapse back toward the ground. This sudden shift can scatter hot embers in all directions, creating new ignition points and complicating firefighting efforts. The day-night cycle also influences how fire crews plan their strategies. Knowing that fires typically slow down at night, firefighters often use this time to strengthen containment lines, conduct backburns, or rest and regroup for the next day's challenges. However, if strong winds or low humidity persist through the night, these plans can quickly unravel, as was the case during the Griffith Park fire. Beyond its physical effects, the day-night cycle also plays a role in human behavior during wildfires. During the day, communities near a wildfire may be more alert and responsive to evacuation orders, thanks to the visibility of flames and smoke. At night, however, darkness can create a false sense of security or lead to delayed responses. In some cases, residents may underestimate the fire's proximity, assuming that cooler nighttime conditions mean the danger has passed. On the other hand, night also brings unique challenges for emergency responders. Limited visibility makes it harder to navigate rugged terrain, locate fire hotspots, and coordinate efforts. Advances in technology, such as thermal imaging drones and night vision equipment, have helped address some of these challenges, but they can't completely eliminate the difficulties posed by working in the dark. The day-night cycle's impact on wildfires isn't limited to its immediate effects. It also interacts with longer-term climatic patterns. For example, in areas experiencing prolonged heat waves, the usual nighttime cooling may not occur. Instead, temperatures remain high even after sunset, creating what scientists call thermal nights. These conditions can extend the window of time in which wildfires remain active, increasing their overall intensity and duration. Understanding how the day-night cycle influences wildfire behavior is critical for effective management and mitigation. It helps scientists predict when a fire is likely to spread rapidly and when it might slow down. This knowledge allows firefighters to allocate resources more efficiently and develop strategies that take advantage of the natural rhythms of Earth's rotation. The Griffith Park fire provided a clear illustration of these dynamics. During the day, soaring temperatures and low humidity drove the fire's rapid growth, while the collapse of smoke columns at night created new challenges for firefighters. By studying these patterns, experts can improve response strategies for future wildfires and potentially save lives and property. But while the day-night cycle plays a significant role in wildfire behavior, it's only one part of the story. To fully understand wildfires, we must also consider the broader seasonal changes driven by Earth's axial tilt. These shifts not only determine when fire seasons occur, but also shape the conditions that make wildfires more or less likely to ignite and spread. Let's explore these connections in the next section. Seasonal changes and wildfire behavior. Seasons, shaped by Earth's axial tilt, play a defining role in the behavior and frequency of wildfires. Earth's axis is tilted at an angle of 23.5 degrees relative to its orbital plane, and this tilt gives rise to the seasons. As Earth orbits the Sun, different regions receive varying amounts of sunlight throughout the year, creating cyclical changes in temperature, precipitation, and vegetation, all of which influence wildfire dynamics. In many regions prone to wildfires, such as California, Australia, and the Mediterranean, the changing seasons dictate when and where fires are most likely to occur. Summers are often the most dangerous time for wildfires. The combination of high temperatures, low humidity, and reduced rainfall during these months dries out vegetation, creating vast expanses of highly flammable material. This natural cycle, driven by the axial tilt, has long been understood by fire managers and scientists. But climate change is now amplifying these seasonal patterns in alarming ways. Let's start with California, one of the most wildfire-prone areas in the world. Summers in this region are dry and hot, a direct result of Earth's axial tilt and its position in orbit. By late summer, vegetation has typically dried out completely after months of limited precipitation. These conditions set the stage for devastating fires, such as the Griffith Park fire in December 2024. While December is technically winter, the preceding months of high temperatures and drought had left the landscape as dry and flammable as it would be during peak summer months. Seasonal changes also influence wind patterns, which are critical drivers of wildfire spread. In California, the transition from summer to autumn brings the infamous Santa Ana winds. These winds, fueled by high-pressure systems over the Great Basin, blow hot, dry air toward the coast. They are strongest in autumn when the axial tilt positions California to experience significant pressure differences between inland deserts and coastal regions. These winds fan flames and push wildfires rapidly across the landscape, as seen during the Griffith Park fire, where embers were carried miles ahead of the fire line, igniting new blazes. Australia provides another striking example of how seasonal changes shape wildfire risk. In the southern hemisphere, summer peaks between December and February, coinciding with Earth's tilt positioning the southern part of the globe to receive the most direct sunlight. During this time, high temperatures and dry conditions dominate much of Australia's landscape, making it highly susceptible to bushfires. The Black Summer of 2019 to 2020, which burned over 18 million hectares, was a stark reminder of how seasonal shifts driven by Earth's tilt can create perfect conditions for massive fires. But it's not just summer that matters. The preceding seasons play an equally crucial role in determining wildfire behavior. For example, wet winters and springs, while beneficial for short-term water supplies, can lead to explosive wildfire seasons later in the year. How? These wet seasons often cause a surge in vegetation growth, especially grasses and shrubs. When summer arrives, this lush growth dries out, creating an abundance of fuel for fires. This pattern, known as the grass fire cycle, is particularly evident in places like California and the Great Plains of the United States. Earth's axial tilt also impacts precipitation patterns, influencing the timing and severity of wildfire seasons. In Mediterranean climates, which include parts of California, Australia, and southern Europe, the tilt creates a distinct wet-dry seasonal cycle. Wet winters saturate the ground and promote vegetation growth, while dry summers strip the land of moisture, leaving it vulnerable to ignition. These seasonal rhythms are consistent, but they are becoming more erratic due to human-driven climate change, which is altering rainfall patterns and extending the length of fire seasons. Another critical factor influenced by seasonal changes is the behavior of fire itself. Fires burn differently depending on the time of year and the type of vegetation available. In summer, fires tend to be fast-moving and surface-level, burning through dry grasses and shrubs. In autumn and winter, fires can smolder longer, consuming heavier fuels like logs and leaf litter. This variability, driven by seasonal conditions, complicates firefighting efforts and requires different strategies depending on the time of year. Historically, humans have adapted their activities to align with these seasonal changes. Indigenous peoples around the world have long understood the rhythms of Earth's seasons and used controlled burns to manage fire-prone landscapes. For example, many Native American tribes in California used prescribed burns during the cooler, wetter months to reduce fuel loads. However, modern human activity is disrupting these natural cycles. Climate change, driven by the burning of fossil fuels and deforestation, is amplifying the effects of seasonal changes. Summers are becoming hotter and drier, while winters are shorter and less predictable. These shifts are extending fire seasons in many regions, turning what were once seasonal events into year-round threats. In California, for instance, the fire season now starts earlier in spring and extends well into winter, as seen with the Griffith Park fire. One of the most alarming consequences of these changes is the increasing frequency of compound events, where multiple factors align to create extreme wildfire conditions. For example, a wet winter followed by an unusually hot summer can produce dense vegetation that becomes highly flammable, leading to massive fires. These compound events are becoming more common as Earth's natural cycles interact with human-induced climate change, creating conditions that were once rare or unprecedented. Understanding the relationship between Earth's axial tilt, seasonal changes, and wildfire behavior is crucial for predicting and managing these events. By studying how seasons influence temperature, precipitation, and vegetation, scientists can develop models to forecast fire risks and help communities prepare. For example, satellite imagery and climate models are now used to monitor vegetation growth and dryness, providing early warnings for regions at high risk of wildfires. Despite these advancements, the challenge remains immense. Seasonal changes, while predictable, are becoming more extreme and less reliable due to the accelerating impacts of climate change. This unpredictability makes it even more important to integrate traditional knowledge with modern science to create resilient landscapes and communities. The story of Earth's seasons is one of both beauty and power. The axial tilt that gives us summer, autumn, winter, and spring also shapes the conditions for wildfires, reminding us of the intricate connections between our planet's movements and the forces that govern life on Earth. But the story doesn't end here. To fully understand wildfire behavior, we must also consider the grander cycles of Earth's movements, those dictated by its orbit around the Sun. Let's explore this in the next section. Orbital dynamics and climate patterns. While Earth's daily rotation and axial tilt create the cycles of day and night and the seasons, there is another, grander rhythm that shapes our planet's climate and, in turn, influences wildfire activity: orbital dynamics. These subtle yet powerful shifts in Earth's orbit around the Sun unfold over thousands of years, shaping long-term climate patterns and creating conditions that directly impact wildfires. To understand these dynamics, we need to look at the Milankovitch cycles, a set of 3 long-term changes in Earth's orbital geometry named after Serbian astronomer Milutin Milankovitch. These cycles, eccentricity, axial tilt, and precession, work together to influence the amount and distribution of solar energy Earth receives over time. While they operate on timescales far beyond human lifetimes, their effects are etched into Earth's geological and climate history, including the history of wildfires. Let's start with eccentricity, the first component of the Milankovitch cycles. Eccentricity refers to the shape of Earth's orbit around the Sun. Over a period of about 100,000 years, Earth's orbit shifts between being nearly circular and slightly elliptical. When the orbit is more elliptical, the distance between Earth and the Sun varies more significantly throughout the year. This variation can cause differences in seasonal intensity, with some regions experiencing hotter summers and colder winters. These changes, while gradual, influence vegetation growth, moisture availability, and ultimately, the risk of wildfires. For instance, during periods of high eccentricity, regions like the western United States may experience longer, drier summers due to increased solar radiation. Over thousands of years, these conditions can lead to an accumulation of dry vegetation, creating a landscape primed for fire. Historical records, including charcoal deposits and sediment layers, reveal that fire activity often peaks during these warm, dry periods associated with high eccentricity. The second component of the Milankovitch cycles is axial tilt, also known as obliquity. Over a 41,000-year cycle, Earth's axial tilt oscillates between about 22.1 and 24.5 degrees. This tilt affects the intensity of the seasons. When the tilt is at its maximum, summers in both hemispheres become hotter, while winters are colder. Conversely, when the tilt is at its minimum, seasonal differences are less pronounced. This fluctuation in seasonal intensity has a direct impact on wildfire behavior. During periods of greater tilt, hotter summers can lead to prolonged droughts and dry conditions, increasing wildfire risks. This has been observed in ancient climate records, where higher axial tilt aligns with increased evidence of wildfires, such as larger deposits of charcoal in sediments. In contrast, periods of lower tilt often correspond with cooler, wetter conditions that suppress fire activity. Finally, there is precession, the slow wobble of Earth's axis, which completes a full cycle approximately every 26,000 years. Precession changes the timing of the seasons relative to Earth's position in its orbit. Imagine a scenario where precession aligns Northern Hemisphere summers with the point in Earth's orbit closest to the Sun. This alignment, known as perihelion, would amplify the heat of summer, creating conditions ripe for wildfires. Conversely, if summer occurs when Earth is farthest from the Sun, known as aphelion, the reduced solar intensity would lead to cooler, milder conditions, lowering the risk of wildfires. These three components of the Milankovitch cycles, eccentricity, axial tilt, and precession, don't operate in isolation. Instead, they interact in complex ways to create long-term climatic patterns. These interactions help explain the cyclical nature of wildfires observed in Earth's geological history. But how do these ancient cycles connect to the wildfires we see today? However, human activity, particularly the burning of fossil fuels and deforestation, is accelerating climate changes that would normally take thousands of years to occur. This acceleration is pushing Earth's natural systems out of balance, amplifying the conditions that lead to wildfires. For example, the prolonged droughts in the western United States, which contributed to devastating fires like the Griffith Park Fire of 2024, are partially influenced by long-term climate trends tied to orbital dynamics. These natural dry periods are now being intensified by rising global temperatures, which increase evaporation rates and reduce water availability. The result is a landscape that is drier, hotter, and more susceptible to fire than ever before. Another connection between orbital dynamics and modern wildfires lies in their influence on ocean currents and atmospheric circulation. Shifts in Earth's orbit can alter the behavior of major systems like the El Niño Southern Oscillation, NSO. which impacts precipitation patterns worldwide. During El Niño years, for instance, the western United States often experiences drier-than-average conditions, increasing the likelihood of wildfires. While ENSO events occur on shorter timescales, their behavior is influenced by the larger, slower rhythms of orbital changes. Understanding how orbital dynamics shape wildfire behavior isn't just about studying the past, it's about preparing for the future. Scientists use data from ancient climate records, combined with modern technology like satellite imagery and climate modeling, to predict how wildfire risks will evolve in a warming world. By identifying regions that are most vulnerable to the combined effects of orbital dynamics and human-induced climate change, we can take proactive steps to reduce fire risks and protect ecosystems. However, this understanding also comes with a warning. The natural cycles that have shaped Earth's climate for millions of years are now being disrupted by human activity. The rapid pace of climate change is outstripping the slow rhythms of the Milankovitch cycles, creating conditions that are unprecedented in Earth's history. To address this crisis, we must not only mitigate the impacts of human actions but also deepen our understanding of the natural processes that govern our planet. The story of Earth's orbit is a reminder of the delicate balance that sustains life. These orbital dynamics, while imperceptible in our daily lives, have a profound impact on the conditions that shape wildfires. By studying these grand cycles, we gain a deeper appreciation for the interconnected systems that define our world, and the urgent need to protect them. In the next section, we'll explore another fascinating aspect of Earth's movements. Let's dive deeper into the long-term influences that continue to shape our planet's fire history. As we look to the future, understanding precession's influence on wildfires is more important than ever. With global temperatures continuing to rise, the natural cycles of precession and axial tilt will intersect with human-induced climate change in ways that are difficult to predict. These interactions could lead to unprecedented fire conditions, challenging our ability to respond and adapt. Ultimately, precession reminds us of the interconnectedness of Earth's systems. The slow wobble of our planet's axis, imperceptible in our daily lives, shapes the climates that support life and influence the forces of destruction. In the next section, we'll explore how another celestial force, the Moon, affects wildfire behavior in surprising and often overlooked ways. From its gravitational pull to its phases, the Moon's influence on Earth's systems extends far beyond the tides. Let's uncover the lunar connection to fire in the following chapter. The Moon's gravitational pull and its influence on wildfire behavior. When we think of the Moon, our minds often turn to its beauty in the night sky or its role in creating ocean tides. But the Moon's influence extends far beyond the movement of water. It also plays a subtle yet significant role in shaping Earth's atmosphere and, indirectly, the conditions that drive wildfires. The Moon's gravitational pull creates tidal forces, not just in the oceans, but also in the atmosphere. These atmospheric tides are much less visible than ocean tides, but their impact is no less real. They cause slight shifts in air pressure and wind patterns as the atmosphere responds to the Moon's gravitational tug. Over time, these movements influence the distribution of heat and moisture in the air, two critical factors that affect wildfire behavior. During a full moon or new moon, the gravitational forces of the Moon and the Sun align. amplifying their combined effect. This phenomenon, known as a spring tide, not only leads to higher ocean tides, but also enhances atmospheric tides. These amplified tides can result in subtle changes in atmospheric pressure, affecting the movement of air masses and the distribution of humidity. In regions prone to wildfires, these shifts can create drier conditions, increasing the risk of ignition and the spread of fires. Consider the role of the moon during periods of prolonged drought, a common precursor to wildfires. In these dry conditions, even minor changes in atmospheric moisture can have significant consequences. For example, during a full moon, the alignment of gravitational forces can draw moisture away from the lower atmosphere, leaving vegetation even drier and more susceptible to ignition. While these effects are subtle, they contribute to the delicate balance of factors that determine wildfire risks. But the moon's influence doesn't stop with atmospheric tides. Its phases also play a crucial role in shaping human responses to wildfires, particularly at night. During a full moon, the increased brightness allows for greater visibility in firefighting efforts. Firefighters can better spot embers, track the fire's perimeter, and coordinate their strategies. In contrast, during a new moon, when the night sky is darkest, firefighting becomes significantly more challenging. Limited visibility makes it harder to navigate rugged terrain, identify hotspots, and direct resources effectively. The Griffith Park fire in Los Angeles, which erupted in December 2024, offers a compelling example of how the moon can impact wildfire management. The fire coincided with a waxing gibbous moon, providing firefighters with a natural source of light during nighttime operations. This added visibility was critical in allowing crews to establish containment lines and prevent the fire from spreading further into residential areas. Interestingly, the moon's gravitational pull also affects the behavior of smoke plumes. During certain lunar phases, the alignment of gravitational forces can create slight changes in atmospheric stability. These changes influence how smoke rises and disperses, impacting visibility for both firefighters and nearby communities. In some cases, the gravitational influence of the moon can cause smoke plumes to linger longer in the lower atmosphere, creating hazardous air quality conditions. Beyond its physical effects, the moon has a profound psychological impact during wildfire events. Studies have shown that full moons can influence human behavior, often increasing alertness and a sense of urgency. This heightened awareness may play a role in how communities respond to wildfire threats. For instance, during a full moon, residents may be more likely to notice the glow of approaching flames or the smell of smoke, prompting quicker evacuation responses. Conversely, the darkness of a new moon can create a sense of isolation and fear, potentially delaying critical decisions. The moon's influence on wildfires isn't limited to the present day. It has shaped human understanding of fire for thousands of years. Ancient civilizations often link the moon's phases to fire-related rituals and practices. In many cultures, the full moon was seen as a time of renewal, a period to clear old growth and make way for the new. This symbolic connection mirrors the ecological role of wildfires, which, despite their destruction, play a critical role in regenerating ecosystems. Indigenous communities around the world have long recognized the moon's subtle influence on the natural world. In some Native American traditions, for example, the moon was thought to guide the timing of controlled burns. These burns, often conducted under the light of a full moon, were carefully planned to align with lunar phases that maximized safety and effectiveness. By understanding the moon's rhythms, these communities developed sustainable practices that reduced the risk of catastrophic wildfires. Modern science is beginning to validate some of these ancient insights. For instance, researchers have found that lunar phases can affect the behavior of atmospheric tides and humidity levels, influencing wildfire conditions in measurable ways. While the differences may seem small, they highlight the interconnectedness of Earth's systems and the importance of understanding even the most subtle influences. As human activity accelerates climate change, the natural cycles that have governed Earth for millennia are being disrupted. Rising global temperatures and shifting weather patterns are amplifying wildfire risks, making the moon's influence just one piece of a much larger puzzle. The interplay between the moon's gravitational pull, atmospheric tides, and human responses underscores the complexity of wildfire dynamics. By studying these connections, scientists and fire managers can develop more effective strategies to predict and manage wildfires. For example, understanding how lunar phases impact nighttime firefighting efforts could lead to new approaches in resource allocation and planning. Ultimately, the moon's influence on wildfires reminds us of the intricate balance that sustains life on Earth. As we continue to explore the forces that drive wildfires, from Earth's movements to the moon's rhythms, we gain a deeper appreciation for the interconnected systems that define our planet. Cultural and historical significance of the moon and wildfire. The moon has always held a profound place in human culture, symbolizing transformation, renewal, and the cycles of life. Its phases, from the full moon to the new moon, have been closely tied to the rhythms of nature, serving as a celestial clock that guided everything from agricultural practices to spiritual rituals. This connection becomes even more apparent when we consider the moon's influence on fire, both as a natural force and as a tool shaped by human hands. Across ancient civilizations, the moon was often associated with the dual forces of destruction and renewal. In Greek mythology, Artemis, the goddess of the moon and the wilderness, embodied this duality. Her domain was the untamed world, where fire played a critical role in shaping ecosystems. Wildfires, like Artemis herself, were seen as both destructive and regenerative, clearing old growth to make way for new life. Similarly, in Hindu mythology, Chandra, the moon god, was linked to the tides and seasonal cycles that influence fire activity. These stories reveal an intuitive understanding of the moon's role in shaping Earth's natural patterns. The full moon, with its bright and steady light, has long been viewed as a time of purification and renewal. For centuries, communities around the world would light ceremonial fires under its glow, symbolizing the cleansing of the old to make way for the new. These rituals were not just symbolic, they were deeply practical. In many agricultural societies, full moons marked the ideal time for controlled burns. The light of the moon allowed farmers to safely clear fields of old vegetation, preparing the land for planting while reducing the risk of uncontrolled wildfires. These practices demonstrate how humanity has long aligned its activities with the cycles of the moon. Indigenous communities have also recognized the moon's influence on fire management. In Australia, Aboriginal peoples practiced fire stick farming, using fire as a tool to shape the landscape. These controlled burns were often timed to coincide with specific lunar phases, particularly the full moon. when the added light made the process safer and more effective. This practice not only maintained healthy ecosystems, but also reflected a deep respect for the interconnectedness of natural cycles. In North America, Native American tribes similarly used the moon's phases to guide their land management practices. They understood that the timing of burns could influence plant growth, wildlife activity, and the overall balance of the ecosystem. The connection between the moon and fire extends beyond the practical to the symbolic. In many cultures, the moon is seen as a guiding force, a silent witness to humanity's struggles and triumphs. This symbolism is particularly poignant during wildfires, when the glow of the moon serves as a reminder of resilience and renewal. For communities recovering from fire, the sight of a full moon rising over a burned landscape can be a powerful symbol of hope, reinforcing the idea that life will return, just as it has for millennia. In modern times, science has begun to validate many of the traditional practices and beliefs tied to the moon and fire. Researchers have found that lunar phases influence atmospheric tides, humidity levels, and even the behavior of plants and animals. These subtle effects can impact wildfire conditions, shaping the timing and intensity of fire activity. For example, the gravitational pull of the moon during a full moon can create slight changes in atmospheric stability, affecting how smoke plumes rise and disperse. While these effects may seem minor, they add another layer of complexity to the already intricate dynamics of wildfires. Wildfire management today can also benefit from the insights gained through centuries of observing the moon's influence. Timing nighttime operations to align with the full moon, for instance, can improve visibility and safety for firefighting crews. Similarly, understanding how lunar phases affect wildlife behavior can inform strategies for minimizing the impact of wildfires on ecosystems. By integrating traditional knowledge with modern science, we can develop more effective and sustainable approaches to managing fire in a changing world. The cultural significance of the moon is not just a relic of the past. It continues to shape how we understand and respond to natural phenomena like wildfires. From its role in guiding ancient rituals to its influence on modern fire management, the moon remains a vital part of our relationship with the Earth. Its phases remind us of the cyclical nature of life, the interconnectedness of natural systems, and the resilience of both human and ecological communities. As we face the growing challenges of wildfires in a warming world, the wisdom of the moon offers a timeless perspective on adaptation and renewal. The moon's influence on fire is a testament to the enduring connection between humanity and the cosmos. It is a reminder that, even in the face of destruction, there is always the promise of rebirth. As we continue to study the moon's role in shaping wildfire behavior, we gain not only a deeper understanding of the natural world, but also a greater appreciation for the delicate balance that sustains life on our planet. Wildfires are not isolated events. They are the result of complex interactions between natural systems and the profound changes humans have made to our planet. As global temperatures rise, the delicate balance that once regulated fire cycles is being disrupted, creating a cascade of effects that magnify the frequency and intensity of wildfires. Understanding these dynamics is essential to addressing the growing threat they pose to ecosystems, communities, and the global climate. One of the primary drivers of this shift is global warming, fueled by the release of greenhouse gases like carbon dioxide and methane. These gases trap heat in the atmosphere, raising average temperatures across the planet. In wildfire-prone regions such as California, Australia, and the Mediterranean, hotter summers and prolonged droughts have turned landscapes into tinderboxes, where even a small spark can ignite devastating fires. The Griffith Park fire in Los Angeles, which occurred in December 2024, serves as a vivid example of this dynamic. But the story of wildfires doesn't end with their ignition. Fires themselves contribute to climate change, creating a dangerous feedback loop. When forests burn, they release massive amounts of carbon dioxide into the atmosphere, intensifying the greenhouse effect. This additional carbon drives global temperatures even higher, setting the stage for more frequent and severe fires in the future. The Amazon rainforest, often referred to as the lungs of the planet, exemplifies this cycle. Fires there have transformed portions of the forest from carbon sinks, absorbing carbon dioxide, into carbon sources, accelerating climate change. Rising temperatures have also lengthened fire seasons around the world. Historically, wildfires were confined to specific times of the year, such as late summer and early autumn. Today, those boundaries have blurred, and fire seasons have expanded dramatically. In California, for example, what was once a seasonal phenomenon is now a year-round threat. Fires that occur outside the traditional season stretch firefighting resources thin and leave little time for recovery and preparation between events. This trend is mirrored globally, from Australia's bushfires encroaching on the wet season to Siberian wildfires igniting earlier each year as the Arctic warms. Human activities have also reshaped the landscapes where wildfires occur. Urban sprawl has pushed development into fire-prone areas, creating what's known as the wildland-urban interface. Here, human infrastructure and activities provide additional ignition sources, while the removal of natural fire breaks, such as wetlands or intact forests, increases the likelihood of fires spreading. This convergence of human habitation and natural fire cycles heightens the risk to both people and ecosystems. The relationship between wildfires and the atmosphere is another critical factor. Fires release massive amounts of smoke and particulate matter, which can influence weather patterns and precipitation. For instance, aerosols from wildfire smoke can alter cloud formation, reducing rainfall in affected regions. This lack of precipitation further dries out vegetation, increasing the likelihood of more fires in the future. These atmospheric effects demonstrate how wildfires not only respond to climate conditions, but also actively shape them. Perhaps most alarming is the potential for wildfires to push ecosystems past their tipping points. In some regions, fires are occurring so frequently that forests and other ecosystems are losing their ability to recover. When this happens, areas that once absorbed carbon dioxide begin emitting it, further exacerbating climate change. These tipping points could have profound consequences for global climate regulation, making it even more urgent to address the root causes of wildfire escalation. Breaking this cycle requires a multifaceted approach. Reducing greenhouse gas emissions is a critical first step. By transitioning to renewable energy sources, protecting carbon sinks like forests and peatlands, and adopting sustainable land use practices, we can slow the pace of global warming. However, mitigation alone is not enough. We must also adapt to the new realities of a warming world. Improved land management practices, such as prescribed burns and the restoration of natural fire breaks, can help reduce the severity of wildfires. Ultimately, wildfires remind us of the interconnectedness of Earth's systems. They highlight how changes in one part of the system, whether from natural processes or human activity, can ripple across the planet, creating widespread and often devastating effects. By understanding and addressing the synergistic effects of natural and human-induced factors, we can begin to break the cycle and reduce the impact of wildfires on our world. As we move forward, integrating science, Traditional ecological knowledge and global collaboration will be key to mitigating the wildfire crisis. As wildfires become more frequent and intense, the need for accurate forecasting and innovative solutions has never been greater. These fires, fueled by both natural processes and human-induced climate change, pose a growing threat to ecosystems, communities, and the global climate. Understanding the science behind wildfire behavior and applying cutting-edge technology can help us anticipate and mitigate these events more effectively. Forecasting wildfires begins with understanding the conditions that make them possible. Temperature, humidity, wind patterns, and vegetation health are critical factors. By studying Earth's axial tilt, orbital dynamics, and long-term climate cycles, scientists are uncovering patterns that help predict fire risks decades in advance. For instance, changes in Earth's axial tilt, or obliquity, influence the intensity of seasons, creating hotter, drier summers that increase the likelihood of wildfires. These insights allow us to identify at-risk regions and plan accordingly. Satellite technology plays a crucial role in modern wildfire forecasting. Satellites like NASA's Terra and Aqua continuously monitor Earth's surface, providing real-time data on temperature, vegetation, and active fire locations. This data feeds into predictive models, helping us understand how fires might evolve and spread. These advancements not only improve forecasting, but also enhance the ability of firefighting agencies to allocate resources efficiently. Emerging research on the Moon's influence on Earth's systems is also shedding light on wildfire behavior. The Moon's gravitational pull affects atmospheric tides and humidity levels, subtly influencing conditions that contribute to fire risks. During certain lunar phases, changes in atmospheric pressure and moisture can create environments that either exacerbate or suppress wildfire activity. While this field is still developing, incorporating lunar cycles into forecasting models could improve our understanding of wildfire dynamics. Artificial intelligence and machine learning are transforming how we predict and respond to wildfires. These technologies can analyze vast amounts of data, identify patterns, and generate predictions with remarkable speed and accuracy. By combining historical fire data with real-time satellite imagery and weather forecasts, AI-powered systems can pinpoint areas at greatest risk. Machine learning models also simulate how fires might spread under different conditions, providing valuable insights for evacuation planning and resource deployment. But forecasting alone isn't enough. Proactive land management strategies are essential for reducing wildfire risks. Prescribed burns, for example, mimic natural fire cycles by removing excess vegetation before it becomes fuel for larger fires. Restoring natural fire breaks like wetlands and grasslands is another effective approach, as these ecosystems slow the spread of flames and provide safe zones for wildlife. In urban areas, creating defensible spaces around homes and infrastructure can significantly reduce fire damage. Technology is also revolutionizing how we fight wildfires. Drones equipped with thermal imaging cameras can identify hotspots and monitor fire behavior in real time, allowing crews to adjust their strategies. These drones can operate in conditions that are too dangerous for human firefighters, such as areas with dense smoke or extreme heat. Early detection systems, which use sensors to monitor temperature, humidity, and air quality, can alert authorities to potential fires before they escalate. By combining these technologies with AI, we can enhance our ability to detect and respond to wildfires more effectively. Global collaboration is critical in addressing the wildfire crisis. Countries facing similar challenges, such as Australia and the United States, have partnered to exchange knowledge and resources, sharing expertise on firefighting techniques, prescribed burns, and advanced technologies. These partnerships highlight the importance of viewing wildfires as a global issue, requiring collective action. Building resilience at the community level is equally important. Educating residents about fire risks and preparedness measures can save lives and reduce property damage. Programs that teach individuals how to create defensible spaces, prepare evacuation plans, and protect their homes can empower communities to face wildfires with greater confidence. Investment in fire-resistant infrastructure, such as underground power lines and fireproof building materials, can also minimize the impact of wildfires on vulnerable areas. Ultimately, the solution to the wildfire crisis lies in adopting a holistic approach that combines science, technology, and traditional ecological knowledge. Indigenous communities have long practiced sustainable land management techniques that align with the natural rhythms of their environments. By integrating these practices into modern strategies, we can create more effective and culturally respectful solutions. Wildfires remind us of the interconnectedness of Earth's systems. They are both a symptom and a cause of the broader challenges facing our planet, from climate change to habitat loss. Addressing these challenges requires innovation, collaboration, and a commitment to restoring balance to the natural world. By investing in forecasting technologies, proactive land management, and community resilience, we can reduce the impact of wildfires and protect the ecosystems that sustain life on Earth. As we look to the future, the tools and knowledge we have today offer hope for a better tomorrow. By embracing science and fostering global cooperation, we can build a world where wildfires are managed, not feared. A world where humanity and nature coexist in harmony. Wildfires are shaped by a complex interplay of natural forces and human activity. From Earth's rotation and its influence on wind patterns, like the Santa Ana winds in California, to the cycle of day and night that affects fire behavior, the planet's movements have a profound impact on how fires ignite and spread. While cooler nights once slowed fires, warming temperatures are disrupting this rhythm, leaving less time for recovery and containment. Earth's axial tilt drives seasonal variations, creating prolonged dry periods in fire-prone regions like California and Australia. Combined with human-induced climate change, these dry seasons are becoming hotter and longer, increasing the risk of devastating wildfires. Similarly, Earth's elliptical orbit and Milankovitch cycles have long influenced climate and fire behavior. But today, rapid global warming is amplifying these natural processes, pushing ecosystems beyond their limits. The moon also plays a role, subtly shaping wildfire dynamics through its gravitational pull and phases. A full moon provides vital light for nighttime firefighting, aiding crews in managing fire lines and navigating rough terrain. During the Griffith Park fire in Los Angeles, lunar illumination proved invaluable in combating the fast-moving flames. But these natural cycles are now intertwined with human actions. Rising temperatures, deforestation, and urban expansion have intensified wildfire risks, creating a feedback loop where fires release carbon, further warming the planet and fueling more fires. Understanding these connections helps us predict and manage wildfires more effectively, blending traditional ecological knowledge with advanced technology like satellite monitoring and AI. In summary, wildfires are a powerful reminder of Earth's interconnected systems. By aligning our actions with the planet's natural rhythms, we can mitigate the risks of these destructive events and create a more balanced coexistence with nature. Wildfires are becoming more frequent, intense, and destructive, driven by natural forces and human activity. As these threats grow, the need for research into wildfire behavior and mitigation has never been more critical. Research helps us understand the connections between Earth's natural systems and fire dynamics. For example, studying how Earth's axial tilt and orbital cycles influence climate patterns allows scientists to predict long-term wildfire risks. These insights are essential for proactive strategies, like identifying vulnerable regions and reducing fire hazards. Technology is transforming our approach to wildfires. Satellite data and AI now provide real-time monitoring and predict fire behavior with accuracy, enabling faster, more effective responses. By integrating traditional ecological knowledge with modern science, we learn from indigenous practices like controlled burns to reduce fuel loads and improve ecosystem health. Ongoing research is the key to staying ahead of the wildfire crisis. With deeper understanding, we gain tools to protect lives, preserve biodiversity, and combat the challenges of a warming world. By investing in science and innovation, we can create a future where wildfires are better managed, with reduced impacts. The Griffith Park fire of December 2024 was a stark reminder of how quickly wildfires can escalate and the challenges they pose to communities and ecosystems. It highlighted the importance of understanding natural forces like wind patterns and lunar phases, while also addressing human-driven factors like climate change and urban expansion. Moving forward, wildfire management must focus on proactive strategies. This includes integrating advanced technologies, such as AI and satellite monitoring, with traditional practices like prescribed burns. Strengthening community resilience through education, fire-resistant infrastructure, and clear evacuation plans is equally vital. By combining science, innovation, and collaboration, we can better prepare for the growing threat of wildfires. The lessons of the Griffith Park fire underscore the need for immediate action and long-term commitment to protecting our planet and its people from these devastating events. Thank you for watching. Don't forget to like, subscribe, and share your thoughts in the comments below. Until next time, keep exploring.